that in looking at this, what we had are typical ranges. These are percentiles related to classroom desks, related to cafeteria tables, and related to bathroom areas as well. And these are the percentiles moving across of the ATP readings on the different surfaces that we're looking at. Now, with that, IICRC took this and they developed these standards, these clean standards, and they had their own. They marked anywhere between 0 to 50 percentile and be effective cleaning if you have that. Somewhat equivocal above that, and then definitely above 75% ineffective cleaning. So these are the designations, and you've got one for each monitor. So it might be high. The three that we use were Hygiena, Charm, and 3M, which are typically often used. There are others, Kikkoman as well. But again, you have to know what monitor you're using. And these standards have that kind of thing. They have the readout for each monitor, depending on what you're looking at. And again, this research was conducted by our university, Gene Cole at Brigham Young at the time, and was funded by Cleaning Industry Research Institute and IICRC. The goals were, what is clean? What are typical ranges of what you're going to find on surfaces? And so there is a clean standard related to schools, and there's a clean standard related to commercial facilities that they developed. This is what they have related to schools. You can see cafeteria tables. This is for the 3M monitor, yeah. And you see what's effective cleaning, and then so on down the line. On the other hand, for commercial, you've got the same sort of thing, but they're looking at effective cleaning. Now, they only have one surface here for commercial. And here, for schools, we're looking at desks, tables, stall doors, sink surroundings, bathroom areas as such. The interesting thing is that when they look, and it's IICRC, when they looked at this and said, I'm going to apply this to commercial, all they looked at were the cafeteria tables, which are, it's kind of fair, but they are the worst in terms of trying to deal with. Because of the fact you've got food residue, and that's going to light up an ATP monitor. So it's kind of a conservatively high level of bar, not that difficult to meet in a commercial facility, should not be. And this is what they have again for their clean standard for commercial. And you'll see this if you're looking at it. But it's useful to look at these things to try and understand in your own work, what are you gauging? What do you have when you arrive on site? What are you looking at? What is the level of contamination? How does it rank in terms of typical contamination within a building, within other buildings as well? Is it high? Is it low? And what? And where do you go from there with the cleaning? So clean standards as a whole should ultimately reflect health. Right now they don't. We've got some studies on health. I'll show you one if I have time at the end, and we'll talk about that briefly as well. The interesting thing that we found in those 10,000 measurements, we did a lot of Rodak plates. So we were looking at cultural bacteria as well. And we aligned that with the ATP, and what you see on top here is the ATP, and you see similar reactions with Rodak, which is interesting again. There are different studies that show you cannot relate microbial to ATP reduction. Well, it depends. It depends upon what that surface might be, what application. In schools, it seemed to work out fairly well that we would get a similar reduction with bacteria as we saw for the ATP. And with that, we would collect we also looked at side-by-side ATP to look at how it relates to microbial. And just to see, we looked at qPCR and DNA swab samples. And in doing that, we published on that as well. So I only put these in there so when you get these notes, you could refer to these papers should you be interested. And this was published a few years ago as well. As such, we were looking at that ATP and microbe comparison, and the thing that was fairly interesting is that, actually it's very interesting, is that if you look at the curve related to microbes, on the bottom you've got bacteria, fungi, and I think skin scales or human cells. But you see microbes, and the curve on the bottom is ATP, and they do follow similar trends. So that's useful. So again, ATP doesn't tell you exactly what you have, but it gives you an indication of the microbial layer. It doesn't guarantee that the surface is free of microbes, but those trends are the same as what you would have. And ATP is much easier to do than taking a swab, sending off to a lab, getting a DNA analysis on that, and going from there on what you've got. So it's a good indicator, a rapid indicator again, and that's what it's useful for. Now, what are the caveats? There are a lot of caveats. I mean many, and this is where we could go wrong, okay? And there's no better, I mean, there are a lot of papers, and we publish a lot of papers, and but one excellent paper is one by Ralph Moon. And Ralph, you should take a bow because I love that paper, And Greg Whiteley and I, and all of us, Gene Cole, we all talk about it, and we knock it around, share it, and slander your name anytime we can. No, you've done a great job there. And it summarized some of this that I'm going to get into here. So what are the caveats? Well, the caveats are ATP reflects removal. It doesn't reflect kill. Luminometry by itself does not measure the concentration of microbes on surfaces. It measures organic material. All right? Cleaning with a cloth and then sanitize. Why do we do that? Well, typically with organic dirt, you're going to have higher number of microbes. However, other soil can coat the surface and obscure microorganisms. So when you're cleaning, you don't only spray with a sanitizer or disinfectant, what you might be using, but you want to address first, try to remove the soil layer on top. So clean and then sanitize is the idea here that you're going to be doing. And it's the idea of this. If you look at this, what are we looking at? I have no idea, but I'm looking at a surface, and it may be completely coated with all this dirt and soil and whatever. But if we look closer underneath that surface, we begin to see what those microbes are that might be harbored there. And you've got here what? A crocodile or something like that. So those are the things that we're trying to get to. We're trying to measure and trying to understand and trying to clean. So that's important. Clean first, sanitize afterwards. That's, a key. Now, if you're using ATP, you can't use it on everything. Hard, non-porous surfaces, high-touch objects. That's what acronym there, real quick. Phone lights and such. Stainless steel handrails, desktops, door handles, keyboards. Toilet areas, got to add slot machine, handles, panels, and we're getting ready to publish on a study we did on airports where we took thousands of measurements and hotels. It's very interesting. I don't have time to go into it, but
thank you.
Yeah, you don't want to know. Desks, these are surfaces that you can look at. Toilet areas, ramps, escalator ramps. elevator panels, but I should have had slot machines up there. I just love that. So whoever brought that up, who brought that up? This is great. I'm going to jump into that at another point in time. What do you not want to use ATP on, yet many people use it? Don't use it on porous surfaces. The variability on the sample itself is going to be off the charts. So, gypsum board, plaster, worn surfaces, composite materials, flooring, carpet, all carpet, plaster, popcorn ceilings, you just can't do it. I mean, you can't do it with any sense of reliability. You're going to get a lot of false positives, you're going to get a lot of false negatives. And that's where you're going to go wrong. All right, so, and if you have an enzyme containing cleaning product, don't use ATP because it's going to light it up. It's going to light it up, and you're going to say, oh my gosh, no matter what I do, I'm not getting rid of the bioburden. You actually are, but the cleaner itself is the bioburden. So keep that in mind as well. Other issues with sampling. The variability of the luminometers is tremendous, okay? So each luminometer has its own problems inherent. Other things, spatial considerations. What are you trying to characterize? Are you trying to characterize an entire cafeteria in terms of tables and know how well you're cleaning them? How many samples are you going to have to take? How many surfaces are you going to have to look at? Irregular sized surfaces, you know, shaped surfaces and what? How are you going to sample that consistently? You can't just go and say, hey, I'm going to take an ATP swab, pull up the swab, just and then go over here and just do a little there. It's got to be comparative, all right? So you've got to have a template in terms of what size you're going to sample from. You know, there are many different surfaces that have been used. In our studies, we used 2 inch by 2 inch, 25 square centimeters as a standard template. Some people use 1 inch by 1 inch, 2.5 by 2.5. So centimeters squared, centimeters, 2.5 centimeters, and so you could use that as well, depending on what you're trying to get. But be consistent so you can compare the results. Otherwise, you're going to have to normalize it to a different area for each one, and you don't really want to do that. And how many samples? Is one sample okay? So I'm going to pick a desk there, and that's all I'm going to sample. And on that desk, it's that important. I mean, it's that representative. For the 10,000 samples that we were taking, we took a lot of samples in a typical classroom. At least we would take upwards of 10 different desks and samples on each one of the desks and repeat them to try to get those typical concentrations and what. So, I'm sure some of you are aware of who Greg Whiteley is. He's a professor at Western Sydney University, and he's a practitioner as well in Australia. And we're working on, we've worked together on different research, and he's got an excellent kind of recipe for using ATP and to do it well. So I thought I'd kind of provide that to you here and try and make a cookbook fairly straightforward is how we're going to do that. So with that, kind of stuck here on that. At least the clicker's not working.
Working on it, Bishop.
Okay. Nope.
It's an important slide, that's why I won't know.
There we go. Okay. Step 1. I was going to have everyone push it, see who had the magic, and then we'll ATP them.
I would say roll the batteries.
We're going to determine what sample size. Is it going to be a template of 2 inch by 2 inch, 1 inch by 1 inch, or what, you're going to develop that beforehand. Select the sampling areas. What are you going to be sampling, right? And so the first thing you're going to do, you're going to take matched pairs of samples. You can do it side by side or fairly within the same proximity. I wouldn't do them side by side because of the fact I would do it close because you're going to be cleaning afterwards as well. Okay. There it is. So we're taking side by side. Then you can take one sample, you can take 2 samples, and on that, the other error that Ralph and I were talking about this at lunch is that often the user error in ATP. So if you're taking a sample and you're taking a sample, the reading may be very different on how you're swabbing that area, how you're swabbing that template, right? So you got to roll the swab, and you've got to be sure, okay, we're going to be consistent. We're going to do it so many times horizontal. We're going to go back and forth, and then we're going to go vertically and do that. You've got to cover the area of the temple. But your method may be very different than his method, and that will absolutely affect the outcomes. Both readings are above that cleaning threshold that is preset. It's dirty. Or first reading is high and the second reading is low. Could very well happen. Now you got a false positive. So that's why these matched pairs tell you a lot about what you're doing. And if we plotted it, and we were doing a lot of these, you'd find that sort of thing, that false negative, where the second reading's high, first reading's low. Both of them in the green here, where both of them are within the acceptable range. In the high upper quadrant to the right in the red, those are where both of them did not meet the cleaning threshold. And below, you'd have a false positive where the first swab would be high and the second swab would be low. And you'll find that if you only take one sample, you're going to have all sorts of false positive and false negatives, and you want to avoid that. So the combination of 2 samples can be compared to the third to determine if cleanliness levels can be improved or should be improved. The data reliability is important, and that's pretty cool, is that if you only take one sample, your degree of reliability or acceptable is about 80%. But if you take 2 samples now, we begin to understand better what we're dealing with, and you can use statistics on it, and what you get is up to 96% reliable in terms of ATP outcomes. And you're going to want to do that. That's useful, again, and only a 4% chance of it being unreliable. And the paper goes into that. But that is a simple step-by-step of it, what we're talking about. Avoiding false positive, avoiding false negatives. So, in summary on this, ATP monitoring is not appropriate for other health hazards. So it's not going to be good for inorganics, lead, asbestos, fibers, chemicals as such. We spent about, we started that in 2019, right in the middle where COVID hit, and we had to shut down, and then we had to start back up. So it was very difficult. We had to take a lot of information. So we looked at health data on 40,000 students, and in a very large district. And in doing so, and this had to do with looking at ATP related to enhanced cleaning. So we had control schools on the upper, the dashed line, and we had the intervention schools, and these are simply ATP mean levels throughout the study. And you see, definitely we had an improvement in the schools, the intervention schools, and with that, there was a very significant association between as ATP increases your probability of absence goes up, your probability of GI illness goes up, and so it's difficult to get these kind of data. And I think I may have mentioned this briefly last year, but this study has been published again, and it's worthwhile to take a look at because it does validate the fact that ATP reducing bioburden on surfaces, you're going to have that health impact. And we don't have a lot of that in the literature as a whole. So that study showed there were significant associations between biocontamination and absence due to GI illness. So, and when you say significant associations, that means statistics will indicate that. A very high level of review goes into that to be able to make that statement related to moisture damage. Your industry is, I mean, it's right at the forefront. And I've got a call out for help. We're in the midst of a very large study that's been going on 5 years. And we're looking at remediation of mold in homes. And we're looking at typical fungal ecology, not typical fecal ecology, sorry, on that. But we're trying to get to that. And how many of you know what ERMI is? E-R-M-I, Environmental Relative Mold Index. It's not that great. I mean, that's, and so we're trying to improve upon that. A quick indication that you can go in and determine what is normal fungal ecology. And I know I mentioned that last year, but it's really important that we know that. We understand, because just like Ralph said, at the end of the study, you might have normal fungal ecology after you've done cleaning, but a few months later, you've got all sorts of things that have ensued. And do you have that? And is it a function of the work you did that it is now equilibrated back up, or that you didn't fix something? Or do you still have normal fungal ecology? And then what activities were going on from that one point to this point in time later, 90 days later? So those things are important, and we're working on them. So if any of you are doing mold remediation, I'm calling out to you right now, please contact me, because we are looking for previously remediated homes. So if you are remediated, or you know of homes, especially in the Chicago area or Kansas City or in those regions, we're trying to get, all we're looking for is a quick dust sample in those homes that have been remediated in the past 2 or 3 years.